So, welcome back guys, and as ever, I do hope you and your family are keeping well. So, we're going to look at a new topic today. We're going to look at the topic of light. What light is, what it's made up of, how it travels, and what it does when it hits different surfaces. So, the first thing I wanted to look at is where do we get light from? And you might think, well, that's pretty obvious, but perhaps it isn't. Okay, so we get light from a number of different places. Some of them are obvious and some not quite so obvious. The most common one is hot things. So if you think about it, bonfires you see because they give off light and they're hot. Candle flames give out light. If you heat a horseshoe up and get it really, really hot, it begins to glow red and gives out red light and some infrared too. Okay, the sun, of course, is a big source of light, and things like old-fashioned incandescent bulbs, we call them, that have a piece of wire in them, and that piece of wire gets really, really hot and gives out light. You might think, looking at the sky at the night, you see stars, of course, like our sun, but what about the moon? Okay, well, does that give out light? Okay, well, it's not a source of light. It's not incandescent, it's not hot. What it's doing, of course, is reflecting. And we'll look at that a little bit later and how reflection works. Okay. There's another way that things give out light, and maybe you've seen them. I've certainly seen them out in Honduras. Fireflies that fly around, and you see this flash. You can see them in the UK. This flash of sort of green light, or you may have seen those glow sticks that you snap and then shake. So there are some chemical reactions that give out light as well. Okay, but the main thing for this bit of the course is you understand that light is given out by usually hot things and is reflected off surfaces as well, but those surfaces aren't actually making the light. So let's now look briefly at how you see light. Well, pretty obviously, you look at things with your eyes, and Isaac Newton did quite a lot of work on this, and he did some really crazy stuff that you definitely don't do, and I'm not going to do. He kind of poked his eye, and he poked behind his eye, and he tried to work out what it was that enabled us to see light. Okay, now I'm going to draw a quick and simple diagram that states the obvious, but if you take a surface, maybe a piece of paper that you might be writing on, so there's our piece of paper, and clearly, like my screen at the moment, you can see it, but it's not incandescent, it's not hot. It's not making light itself, like one of Edison's old-fashioned light bulbs. Instead, what it's doing is reflecting light. So, if I draw you here, there you go, and there's your eye, okay, and you're looking at that piece of paper. What's happening is, I'll use a red pen, okay, is the light is hitting the paper, reflecting off, and coming towards you. Okay, and hopefully if you draw it properly, it ends up inside your eye. Okay, now you might think, well, that's pretty simple, but that's a really important diagram, because have you ever seen those pictures, even in cartoons and things, where light's coming out of people's eyes, a sort of sci-fi thing, okay, because you see out of your eyes, and this was much misunderstood. But, of course, it's completely the other way around. That what happens is the light comes into our eyes, and there's a whole load of focusing mechanisms in there that allow us to see a clear picture, a little bit like a camera system in our eye. And the light hits the back of our eye, and it hits a really sensitive place to light called the retina. So we won't take the biology any further, but it's useful for physics that you know that in the back of the eye we have a very sensitive area to light, and that's called the retina. So now let's have a look at how light waves travel. Okay, well, I remember someone saying years ago, I heard that light was made out of waves, and I've never seen those wiggly waves. And yes, indeed, it's actually really, really difficult to show that light is a wave at GCSE level. But I'd like you to think of something that's giving out light as giving out waves, okay, that's kind of wriggle up and down. And the reason we have different colours is some waves are stretched out. In other words, red light comes to you in a wave that's like that, stretched out. It has a long wavelength. Green light, however, is a little bit more pushed together. Still comes at you at the same speed, the speed of light, but it wriggles up and down more per second. And you probably guessed it, all the other colours of the rainbow that are so popular at the moment with the symbols you see for the NHS. But we'll do the blue here, just pick one colour. Blue has a very wiggly wave, a very short wavelength, yep, and a very high frequency. So, light travels in waves, and they're waves of energy. But what we're going to do instead, to make life much simpler, is we're going to just draw these waves as coming at us, like on this diagram, as straight lines. So instead of drawing red light like that, we will just draw it as a ray coming towards us of red light. Exactly the same thing for green light, and exactly the same thing for blue light. And we can do an awful lot of the physics. We can explain a lot of things by saying that light travels in like beams, okay? And we're going to call those light rays. So it's much simpler when we do our diagrams to think about light traveling in a straight line. But I'm going to end this little bit by saying you think of light as traveling in a straight line, but it's quite interesting that if you get something like a laser pointer, and I point it up to the roof, it's actually turned on at the moment, but you can't see it. And I know some of you will be saying, yes, you can see laser pointers. You actually can't see light travelling. Can you just kind of look around the room at the moment and have a look at your lights and your desk light and things like that? You don't see a great beam of light coming out of it, okay? I'll shine the laser pointer on the board now. Okay, what you see is where the light reflects off something. In between, it's totally invisible. And you might say, well, that's a bit weird. But it's obviously invisible because it's going that way and it's not bouncing off anything yet. Once it reflects, better word, once it reflects off something into your eye, you can see it. Now, you might say, well, yeah, I've been to a disco or I've seen car headlights on a foggy night. Sure, but if you think about that one, you shine the ray through the air and there's lots of little particles of smoke or little bits of water vapour in there, like my hand, to reflect it into your eye. So then, of course, you can see the light ray. But we're going to have to use light rays like this to show that kind of invisible bit. But it's pretty clear that something must be travelling from my laser pointer up to the board and then it's reflecting off and coming into my eye. It's carrying light energy, which is one of the reasons I'm not going to point this straight at my eye. It would be really dangerous to do that because there's a lot of energy in light rays. One of the other reasons you should never, never, never look directly at the sun. So let's look a little bit more now at how light travels. So one of the things you might know about how light travels is that it's very, very fast indeed. Okay, it travels at the speed of light. So the speed of light. Okay, and that doesn't answer how fast it travels, but it's incredibly fast. It's 300 million meters per second. Okay, 300 million meters per second. Now, you might know about thunder and lightning, and you see the lightning strike, and then you hear the thunder. the lightning strike light gets to you almost immediately. It's coming at you at 300 million meters per second, 300,000 kilometers a second. It's instant, okay, over that distance. Whereas the sound's much slower. Sound is only about 320, 330 meters per second. It's about 1 million times slower. Now, how do you visualize a number that big? Okay, well, if light could go round in circles, okay, it would go round the Earth, flying like an aeroplane, you could imagine, yeah? The light beam going around the Earth 7 times in a second. Okay, that's just how fast it is, which is incredibly fast. So, for what we do, we consider light to be instantaneous, yeah? It gets to you straight away. It doesn't take time to get to you, okay? Now, one or two of you might say, and I'm going off topic a little bit here, as I always do in lessons, what about stars? Well, yeah, the sun is a very long way away, and it takes about 8 minutes for the light from the sun to get to us. I always say to students that if the sun turned off now, you wouldn't know about it. It would still be a sunny day for another 8 minutes. Thankfully, that's not going to happen. And very, very, very distant stars, well outside our solar system, we've only got the one, obviously, the sun, but stars that are a very long way away, can you imagine how long it takes the light to get from them to us? Yeah, it can take years, or thousands of years, or millions of years if they're a very, very long way away. But still, consider the speed of light to be very, very fast. Okay. The other thing I wanted to look at is, do you remember the laser pointer, or maybe car headlights on like a cloudy sort of evening or what have you, where you see the beams going out? We know that light travels in straight lines. Okay, and it's really simple. I mean, obviously, if I hold my hands up in front of my face, you can still hear me. You might say, well, it's because I've got a microphone on me. Yeah, sure. But if you were in my class, you'd still hear me. And I bet you've never thought about that before. I bet you've never thought that sound can bend around corners. I can go behind my students in class and I can still talk, and even if they're looking forwards, they can still hear me. Sound can bend around corners. But things as big as my hands, okay, don't block out sound, but they do block out light, because light is reflecting off my face and travelling in straight lines. There are some very basic experiments that some students do where they take a piece of paper with a hole in it and another piece of paper with a hole in it, and they move the holes sideways slightly and you can't see through, showing that light goes in a straight line. But what I'd like to do is to look at a slightly bigger scale version of proof that light travels in straight lines. So I often set it as a little challenge to see if anyone can think of kind of the biggest example that light travels in straight lines. And sometimes my students come up with a really good one. They say, night and day, sir. Okay, yeah, absolutely. That if we are in night time, so here's the Earth and we've got the sun here, yep, the light from the sun can land on this half of the Earth, but not this side. That's the bit that's in darkness, that's nighttime. If light bent round corners, the light from the sun at night could come all the way around the back of the Earth and we'd be in day all the time. But I wanted an even cleverer example, okay? And it's the eclipse. Now, the eclipse is really good proof that light goes in straight lines. Okay, so let's draw a little diagram here. So, for an eclipse, maybe you can work out which one it is in a minute. Okay, let's put the sun here. And let's have the Earth over here. Okay, now it's not drawn to scale or anything. I'm just making a teaching point here. So, here's the Earth. And obviously the Earth's way too big, etc. But it just makes the point nicely. Here's the moon. And you know the moon goes around the Earth about once a month. But what happens if the moon is positioned there? Okay, now, it's not an astronomy lesson, this, and it's difficult to understand, but sunlight's hitting the Earth, So this side of the Earth is in daytime, and if I get my ruler and draw light from the sun, a ray coming off the sun like that, okay, and a ray coming off the sun like this. Now we can draw lots of other rays, for example that one, okay, and all the ones that go over here. So maybe I'll add 2 more just to do this properly. So what about a light ray that goes to there, and a light ray that goes to here, okay. Now at the moment my diagram's looking a little bit complicated, but look what happens here. Because light can't bend around corners, okay, during the day, this bit here will be an eclipse. Eclipse means to block out, to kind of get in the way of, okay. And I'll finally ask you, do you know which type of eclipse this is? Okay, to block. What's blocked here? Okay, well, the sun is blocked, so this is a solar eclipse that will happen during the day, and I think you're all too young probably to have seen one of these, okay, but I've certainly seen solar eclipses, and they're quite spectacular. You know, it's a light day, and then suddenly it gets darker and darker and darker, and the moon completely blocks out the light from the sun, and then a few minutes later everything's moving, of course, and the light comes back again. So it just goes dark for a few minutes. Finally on this one, have a look here and here. Not everywhere's in eclipse, so some people are eclipse travellers, and they work out when the next solar eclipse is going to be, and they travel to that point on the Earth's surface, and wearing all the right equipment. Obviously you never want to be looking up at the sun even when it's partially eclipsed, so they wear what looks like very, very dark glasses, better than sunglasses, or they use specialist telescopes, which is better. They can actually see the sun being eclipsed by the moon. So really good proof that light travels in straight lines. So let's now look at what happens when light hits different kinds of obstacles. So if I hold up my water bottle, okay, made of plastic, and the water, I can see straight through it. It lets light go straight through it, just like a normal glass window. So here's the light ray hitting the material, and it goes straight through. And there's the technical word that you probably know already, but there are some others we also need to get used to. So something like clear glass, or my water bottle or water, is transparent to light. It just lets the light pass straight through. Again, I'm going to go off on one now. So when I was at prep school many, many years ago, I remember a teacher asking me, why is the window transparent? Okay, and it was actually one of the most profound questions I've ever been asked, because you find yourself saying, because it is, because light can go through it, because it's not coloured, because it's clear, because it's transparent. But none of that actually explains what's going on inside. And it wasn't really until university that I fully understood how light can get through a solid material without being messed around with, without being stopped. But for this bit of the course, you just need to know that clear materials let light through perfectly. You can't see where the camera is at the moment, but those of you who know my classroom, I'm actually writing on a see-through material here. And that has to be completely transparent. Okay, but what happens if you do this? Okay, my hand or a piece of paper or something like that produces a shadow. So those type of materials, let's draw it there, when we shine light on them, block the light. Okay. They can do it in two ways. They can either kind of hold on to the light and take the energy in and turn it into heat slightly on the surface, or they can reflect the light back at you, but they don't let it go through. And if they don't let it go through, those materials are called opaque. Okay, opaque surfaces. Now, there's one other you need to know, and it's the one you come across most mornings if you have a shower or something. If you look through a bathroom window or the glass of the shower when it's all steamed up, etc., okay, something strange happens. You can sort of see through, yeah, but you can't see through in a very focused way. Okay, what's happening is the light, remember, it's not you looking outwards, okay, you're here, the light coming in from the window or whatever you were looking at kind of gets smudged everywhere. Okay, it kind of gets thrown out in all sorts of directions, and I'm purposefully drawing this just as a bit of a mess. Okay, now those have got to be straight lines, of course, but the picture that you would see, the image, is all kind of messed up. I've got some tracing paper here that I was using for a different video a while ago, and tracing papers like this, I can sort of see through it, but I can't see a clear picture. And this type of material is translucent. Okay, notice the word trans there, trans meaning passing through. So 3 important technical words there. You need to know the difference between a transparent, an opaque, and a translucent material. Right, so now let's look at light reflecting off surfaces. So we're going to do quite a bit of work on this as time goes on. Reflection. And again, it's a word you know well, but it's a word you need to know. Okay. Well, if you ask most people, where do you see a reflection? Okay. I hope they'll come up with maybe 2 different things. They'll either say in a lake when it's really flat and you can see all the trees and things reflected in the lake. Or more typically, of course, you, every morning, I guess, shock yourselves by having a look in a mirror and seeing a reflection of yourself in the mirror. Okay, so what I wanted to do was explain a little bit more about how you see that reflection in the mirror. So imagine a mirror on the wall. So here's the flat surface of the mirror. Now, diagrams, you need to get used to these 2-dimensional diagrams. You're going to look that way, and this is the wall. Okay, so this side is the smooth side of the mirror. So I'm going to do this here to indicate the wall. Okay, so I would look into this that way. Yep. And when light hits a mirror, something quite clever happens. Okay, the light goes in and it bounces off. Wrong word, FJ. Reflects off. So there's a single ray coming in and coming out. Okay, but what about the rest of your face that you're looking at? Okay, or the light from the room? Well, here's another ray coming in. Okay, I've chosen to draw it parallel, and that ray will come out of the mirror like this. And you'll get used to these ray diagrams after a while. And here's another ray, last one, just for the sake of this diagram. Ray number 3, and out it comes. Okay. And the important thing you notice in a flat, smooth surface, so in a mirror, is this. That any light that goes in with some kind of an order, okay, nice and parallel here, comes out with that order. Okay, it's not jumbled up. So if light reflects off your face, okay, then that light will hit the mirror and come off, and your face won't be all weird and distorted unless the mirror's flexed, but we'll look at that later on. Okay, it will come out in an ordered manner. Okay, and this has a particular name. This kind of shiny reflection, okay, is called specular. Specular reflection. Now, I always mention this to people who are in the CCF or the cadets, or some of the girls at school wear like patent leather, really shiny shoes. Yep, that if your shoes aren't shiny, the surface is rough, okay, and you don't see a nice shiny image in them, okay. But if you polish them and polish them and polish them and rub them, you end up making the surface really smooth. So polishing your shoes and rubbing them, or patent leather, is really smooth. It isn't rough, okay. So it has the same effect, just like the surface of a mirror. It's smooth, so any light that comes in a nice ordered fashion comes out in a nice ordered fashion. But it's at this stage that I usually get a student, if they're really thinking, saying, but FJ, you've told us about light reflecting, and if you hold up a piece of white paper, you see the light coming back at you. I can actually reflect that image up there. Okay, my shirt that I'm wearing today reflects all of the light coming off this projector back at you. It's white. It's giving back all the colours that are being thrown at it. But you don't see an image in it. Okay, so if you've got a bit of paper and you look at it, you don't see a picture of your face. So something strange must be going on here. And you need to think about it as being under the microscope. Do you remember what I said about polishing your shoes? Let's look at a bit of paper really close up. Sometimes you can even hear that the surface is slightly rough. Okay, and it's why a pencil works. When you use a pencil on paper, okay, it reminds me of teachers getting their fingernails down the blackboard. When you use a pencil on paper, that rough surface rips the black graphite off your pencil and leaves a line. So paper, yes, it's white, yes, it reflects light, but close up, its surface from all the paper fibres is rough. So you're never going to make a mirror that you want to see yourself in out of paper. Now, the physics doesn't change here. There's no new law of physics, okay? But what happens is, when you shine a ray in like that, okay, that ray reflects off a bit of the paper, maybe that way, and then maybe this way, and ends up there. This ray comes in and maybe reflects up there, and then I don't know where that's going to go, maybe out there, okay. Maybe this ray will come in and end up going that way, okay. And I can draw more and more rays, but you'll notice that the nice parallel rays coming in get kind of jumbled up. So they go off in all kinds of different directions. One of the reasons we draw the number of arrows on them, okay. So if you drew more and more rays here, I usually do loads in class because you put a different ray in, it might come down or it might come straight back at you, but the nice order coming in gets messed up. So here we go. The light's hitting the piece of paper, and that light is then spraying out in all directions. We need a better word for that, okay. It's scattering the light. Okay, and anything that scatters light gives a diffuse reflection. So there we go. You understand a bit more about why mirrors give nice, clear images, and why something like a white piece of paper does reflect light, but that piece of paper doesn't produce a mirror image. So you might well have asked, how did I know where to draw those light rays coming off a mirror? How did I know which way they came off the mirror and which way they went? Okay, well, as in a lot of physics, there's a law that explains which way light rays go when they reflect off surfaces. and you need to know this one. It's not as difficult as it sounds. So what we're going to do now is we're going to go off into the laboratory, and I'm going to do a practical demonstration to show you how light rays reflect off mirrors and what the law of reflection is. Now, if you were here with me, of course, which is a shame that you're not, you'd get the apparatus out too, and it wouldn't be me demonstrating it. I'd give it to you and I'd say, okay, there's a mirror, here are some light rays, have a play and see if you can work out what the law of reflection is. Okay, so I'm in the lab now and I've got my ray kit, so I've got a laser beam of red light here, and I've got myself a plane mirror, and what I'm going to do is I'm going to put this plain straight mirror in front of the laser beam and see what happens. And it's pretty obvious, the light goes basically straight back. But if I turn the mirror, so I'm now going to turn it through an angle, you'll see the light reflects off the mirror. And what's interesting is there's an angle here between these two rays, but if you look carefully, if you look at where the mirror is and draw a 90-degree line from the mirror, it splits that angle in half. And this is really important because if we take the mirrored surface and draw a line at 90 degrees from it, there's an angle here that looks similar to the angle there. So what happens if we turn the mirror through a bigger angle? Well, we've got the mirrored surface, 90 degrees here. We've got an angle there from the line coming out at 90 degrees. We're going to call that the normal. And that angle is the same as this angle here. A lot of people think it's always 45 degrees. There's the 90-degree normal, 45 and 45. But it isn't. And we can make it even bigger. So I could come in maybe at 60 degrees and this would go off at 60 degrees. So what you're looking at there is the fact that when we reflect light in a mirror, the angles are predictable, which means that we can put a mirror in front of a ray and immediately know what angle it's going to come off at. So I'm going to go up to the board and show you that in just a little bit more detail now. So I hope you enjoyed that experiment, and it showed us how light rays reflect off flat mirrored surfaces. Okay, so let's put all that together in our law of reflection. So we'll draw a mirror again, and that's the back of the mirror, the non-reflective side. Okay. And then we can draw any light ray going in. It's best not to draw one that comes straight into the mirror like that. It doesn't really make the point. So we'll have a light ray coming maybe from up here, maybe the light bulb on the roof of the room. Okay. Now, the next bit, I know it's going to come down here. Yeah, I'm a physicist. But where exactly is it going to come down to? So we have a way of doing this, as you know. We're going to draw on a line that's at 90 degrees to the mirror, okay, where the light ray hits. Pupils seem to have real problems working this one out, okay? Find the mirror. It's that easy, okay? And then when you've got the mirror, make sure where the light ray hits, you draw another line that is at 90 degrees to that point. So not there, not there, not there, but there. Okay, 90 degrees to the mirrored surface. And we draw that as a dotted line. Okay, and that dotted line, if you remember, is called the normal. Confusing word, but if you're an architect or an engineer or builder, normal means at 90 degrees too. Okay, so the walls in my lab are normal to the floor. Okay, right. Now, what we're going to do is, and we normally use a protractor, is we're going to measure this angle here. Okay, now it's really important you measure this angle and not that one, this angle here. Okay, and this angle is the angle of the light coming in, so we're going to call it the incident angle. Okay, and then all you do, this is the easy bit, is from the normal coming this way, okay, you know it's going to go like that, you draw the same angle. So let's see if I can get this right. Should really use a protractor, but here we go. Okay, so there it is, reflecting off like that. And this angle in here is going to be exactly the same value. So this angle here, R, is the reflected angle. So the law of reflection is very clear. It says that the angle of incidence is always equal to the angle of reflection. Got to be careful how I say that. So many different words in light. Okay, and what that means is that the angle of incidence, put a little hat on it to show that it's an angle, is always equal to the angle of reflection. So I is always equal to R. Okay, I haven't done too badly on my diagram, but sometimes you need to get a protractor out and actually measure it properly. So let's quickly do some examples of this and see whether you've got the hang of it. Okay, so what I normally do, and you can draw any shape of mirror you like, but we'll just draw plain mirrors, flat mirrors, is if I have a mirror like this, okay, and that's the back of the mirror, and I shine some light in, here we go. So there's a ray of red light coming into the mirror. Okay, complete the diagram to show which way the reflected ray goes. Okay, so remember the golden rule. Find the mirror, find the point where the ray hits it, and draw 90 degrees to the mirror at that point. Mirror, ray, 90 degrees. So that's the bit everyone seems to find difficult. Okay, so thereabouts is the normal line, the normal to the surface, the 90-degree line. And if you remember, the angle of incidence, there it is always equal to the angle of reflection. So I'm going to try my best. It's not so easy up here to do it. I'll come around this side. I think I've got it. There we go. Okay, off the ray goes. And this angle in here, draw it like that, R, is the same size. So the angle of incidence is equal to the angle of reflection. Okay, and I'll just say it again, doesn't matter what shape the mirror is, as long as you've got a shiny surface at GCSE, in goes the ray, measure the angles. Now, I forgot to say, as I always do, if you ask people how light comes out of a mirror to begin with, they nearly always say at 90 degrees. They say, you know, it goes in at sort of 45 and comes out at 45. I hope that diagram shows you straight away that that's not true. There are cases when it can be. And this one up here, okay, the angles there are not 45 degrees either. It's a mistake that a lot of students make. So, just before we finish on that, let's have one more example. And I'll keep it simple. I'll draw my mirror here. And that's, so it's sort of lying on the desk, I suppose, and we're looking down upon it. I'll have a ray coming in. There it is. There's the ray coming in. And I'll label an angle. Okay. So let's make that 30 degrees. I hope some of you are feeling a bit uncomfortable already with this diagram. Okay. And then what the question might ask is, complete the diagram and draw on it the angle of reflection. Made a terrible mistake here on purpose. So, mirror, ray, normal. Okay, so here's the normal. There it is. And I was taught to measure the angle of incidence. If you were here with me and we had a bit more time, I'd explain why that's the important one and not this. I'll do it very quickly. One of the ways you can say is, what happens if the mirror did this and suddenly dropped away? It's not easy to do. There are better reasons, though, why we use that angle. Okay, so we know that I equals R, so I'll try my best. There we go. In exams, please use a protractor and use a ruler. Okay, it's not a guessing game, this one, you have to do it properly. So, you remember this angle here is the angle of reflection, R. And so, if this angle is 30 degrees, okay, designed to catch us out, yeah, 30 degrees, then all the way up to 90 must be the remaining angle. So the angle of reflectance here, the angle of reflection, R, must be So let's put all of this together now and see if we can explain why you see a picture of yourself in a mirror. And it's one of those things that you probably haven't thought much about. So I'd really like you could even pause the video if you're at home now and rush off into your bedroom and bathroom and have a good look at yourself in the mirror and do a few things. Okay, look at the mirror and walk towards it and see what the picture of you in the mirror does, the image. Stand away from the mirror and hold your hand up and move your hand closer and closer to the mirror. See what happens. And finally, I haven't today, but make sure you've got a t-shirt on with something written on it and stand in front of the mirror and see what the writing looks like. Okay? And if you move around, I think you'll have a slightly better understanding of what happens. But the most important thing you should do is, when you look at the mirror, look at it, okay? Keep your head away from it, so, about half a metre away, and just tap on the mirror. And look at where your head is in the image. And it's really weird, because it's not on the surface of the mirror, it's behind it. It's as if you were equally far away looking at yourself. And it's that I'm going to try and explain now. And I'm smiling slightly because there are lots of things in teaching which are really easy. That's why we do it. But there are just a few things that are quite tricky. And I must admit, when I first started teaching, I understood this well, how we get a picture in the mirror. But drawing it, okay? So I'm going to attempt to draw why you can see a picture of yourself in a mirror. You might also, when you've got a moment, want to look at my video, my FJ's Physics video on Pepper's Ghost, which is an absolutely fantastic thing. I won't spoil it for you, but what Pepper's Ghost is all about is when you look in a see-through material, like a sheet of glass. And have you noticed that when you've got the curtains open at night and it's really dark outside, that you don't see outside very well? You actually see a reflection of what's inside the room. Okay, I'm going to spoil it, aren't I? And imagine what happens if you walk around in the room and you see your reflection walking around. But what if someone else did it outside, walked around outside as far away from the sheet of glass as you are in front of it? You might be able to walk straight through their image. That's what Pepper's Ghost's all about, and I'll leave you to look at that little film. So what I've got to do now, I'm avoiding the problem, aren't I? What I've got to do now is try and explain to you why we see an image in a mirror and why it's directly behind the mirror, okay? And it stands upright. Amazing how many people say stuff's upside down in a mirror. What do you mean by upside down? Standing on your head. Don't think so, okay? Writing is swapped side for side. We call that laterally inverted. So let's see if we can explain it, okay? Well, the classic way of doing this, and we would do this in class if you were here, is to imagine something like a candle in front of a mirror, okay? Oh, right back to the start of the video. Yeah? And get the pen to work. It becomes a luminous source of light, something that gives out light, okay? And what we're going to do is draw some rays that come off this candle. So let's have one ray going this way There we go. Okay, and maybe another ray of light coming this way. So there's the second one. Now, follow me on this, but you won't be asked to draw this, I don't think. Well, maybe at GCSE you might. It's quite tricky. Okay, so if you follow all the laws of reflection, okay, you'll see that this light ray comes this way, and this one, it's a slightly steeper angle there, goes that way. Okay, now here's the clever bit, and it's really tricky. You put your eye here, okay? So that's how physicists draw an eye. Do you remember the light goes into your eyes? Okay, so you're here looking, you might be here of course, but this is a good way of drawing it. And the light is coming from the candle, off the mirror and into your eye. But here's the clever bit, okay? Light travels in straight lines and your brain, let me cover that up, doesn't realise that those light rays have bounced off something. It doesn't know that. So what it thinks is that the light came in straight lines from back there. Okay? And what it sees is the flame of the candle, and if you were to draw more rays, the body or the wax of the candle as well. Okay, now I told you I really worried about drawing this diagram. If I was in class with you, I'd take more time over it. Okay, I haven't done it brilliantly, but what you'll notice is following the correct angle laws here, your brain thinks the light rays have come from there. So what's the important point? Well, you get an image here. An image, what you see, of the thing that you look at, the object. It's all technical terms with light, isn't it? Okay. But if you were to go and grab that image, some of you will remember from Pepper's Ghost, if you've seen that video, if you were to try and grab it, your hand would stop here. If you tried to grab your face, you couldn't. The mirror's in the way. This doesn't exist. Okay? It's an optical illusion. There's no light actually coming from behind the mirror. It's an optical illusion. It's virtual. So, what you see in a mirror, the picture, the image, is a virtual image. Okay? These are all technical terms. Now, difficult diagram to draw, but I think the important thing to say here is that if I got a protractor out and got all these angles right here, and then followed those two dotted lines back, that candle would be upright, standing up. Exactly the same distance behind the mirror as the object is in front, okay, and producing a virtual image. So, don't worry too much about the diagram. It's quite complicated, but it's something that you needed to see. So, time for another experiment. And again, I'm sorry you're not here, but if you were, we'd get the apparatus out and you'd do this experiment as well. But I'm going to do it for you so you can see what happens. So we've looked at what happens with plane mirrors, flat mirrors, okay? But what happens when our mirror curves, okay? That one is a concave, it's cave-shaped, you can go inside it, a concave mirror. And this is a convex mirror. It's bent outwards. Now, you might have seen those funny mirrors they have at some fairgrounds that sort of flex in and out and make you look a really funny shape. Very thin and tall, which would be nice for me, or very fat and short, okay? And what they've done there is they've taken a plane mirror and they've flexed it in all sorts of different directions. I'd like you to think, where have you seen convex mirrors before? Those of you who are taught by me know I've got one in the back of the classroom up on the wall there. And where have you seen concave mirrors before? So, the laws of physics for reflection are no different for convex and concave mirrors. So let's go into the lab and I'll show you what happens when we shine light rays on those. So I've got my ray kit here, and I'm going to turn on 3 rays, and let's look at what happens when we use a convex mirror. So a convex mirror is one that we curve towards you. So here we go. Shine the light in, and you can see with a convex mirror it spreads the light out. Or maybe in reverse, I'd like you to think about it as light coming in from a wide field of view, a wide angle, and being brought into those parallel lines and into your eye. So you've now seen what a convex mirror can do. So let's turn it around and have a look at what the concave mirror does. Okay, so now let's have a look at the concave mirror. That's the one that's curved inwards, okay, that's sort of cave-shaped. And this is my favourite one. So I'm going to curve this flexible mirror, it's a bit of plastic mirror, and put it in front of the rays. And I hope you can see what happens there. They all cross over. They're brought into a focus. If I turn it like that, it's not quite so easy to do. You can see the rays crossing over here. Now, you might remember the days of satellite dishes. They were very common on houses until we had cable access TV and broadband and things. But a satellite dish is concave, and there used to be an arm that used to come out the front and have a receiver on it. Okay, and that picked up the rays that came from the satellite. They were microwave rays in this case, similar to light, and it was positioned at the place where the rays all crossed over, where the energy was concentrated, and it can pick up the TV signal. So there we go, the bringing together or focusing of parallel rays in a concave mirror. So finally, let's explain the curved mirrors. So we did 2 different experiments. I normally do the convex, can you remember which one that is? The convex mirror first. So it's curved outwards. So this is the back of the mirror there. Okay, and this is the shiny side. Okay, and this is a very clever mirror. If we take some light like this that comes that way, and some light like that that comes that way, okay, maybe think of it as light from the roof and light from the floor. Then if you draw the normal on and follow all the correct rules, okay, you can get the reflection of these rays. And do you notice, haven't quite got the angles right, but not far off there, okay, that it's taken those very wide rays and it's brought them inwards. So, do you remember the physicist's eye? There's the eye. All it does is it shows you the direction that you're viewing, and you'll notice that these rays travel towards the eye. Now, you would never be able to see right up to the roof and down to the floor at the same time. You wouldn't be able to see right out like that. It's too wide a field of view. I'm going off again on one of my stories. When I have my pilot's medical once a year, the medical examiner always checks that I've got a good wide field of view. So he kind of holds his fingers up and he moves them round and he tells me to tell him when I can see them. And if it was there, I think I'd lose my license, okay? Yeah, I have to be able to see a wide, but not totally 360 field of view. That would be impossible. I'm not an owl, okay? So here we go. So look what it does. It takes rays that are very spread out, up and down and sideways, and it brings them inwards. It brings them inwards into your eye. Okay, so the convex mirror is absolutely brilliant at looking around corners and things. And you see these sometimes on road corners, at junctions and things like that, you know, where a normal flat mirror would allow you to see some of the way around the corner, but a convex one allows you to see a much wider field of view. So finally, let's bring it all together with the concave mirror. Okay, so if you remember, the concave mirror curves like a cave. It curves inwards. There we go. Okay, so I've drawn the back of the mirror there and the shiny side on this side. Now, this is one. It deserves a whole lesson in its own right. Okay, really clever kind of mirror, this one. Imagine if we shine light straight into the centre of the mirror. Okay, I think you can see that'll come straight back at you. But what happens if we shine another parallel ray like that, and maybe another one like this? Okay, so I'll make the middle ray just a little bit clearer. We use exactly the same laws. The angle of incidence equals the angle of reflection. So we've got a normal there, and this one will come down. We've got a normal there, so that one will come down. Go up. Apologies. And here we go. So there it is, going that way. And here's this one reflecting off the curved surface, going that way. They do carry on, of course. Yeah, but most teachers stop them there. So here's this ray. I'll draw 2 arrows on that one. And here's this ray. 3 arrows on that one. 2, 3. And look at that. Okay. This is a really clever mirror. It takes whatever waves, light waves we feed in, and if you can imagine, this is quite complicated, but if you can imagine they come straight back at you until you curve the mirror and bring them inwards, they go to a focal point, a focus point on the mirror. They then carry on, but if you were to put something here, okay, you could pick up all 3 rays concentrated at that point. Okay, I'm going to make a film later on to show how heat can come in. Heat is an invisible light ray. It's infrared and can focus at that point and set fire to something. But more importantly, a use. Okay, a use of this one. Well, what about a satellite dish? Okay. Now, I wonder whether satellite dishes are getting a bit rarer now. We used to all have them on our houses, but you've now got broadband and things like that, cable access TV. But look what happens. If we take waves, they're not light waves, but they're microwaves or radio waves from a transmitter, we can focus them down to one point. But you're saying, hang on, FJ, this is a lesson on light. Well, there are similarities, but let's do it with light. But imagine it in reverse. Imagine if we put a light bulb there. The light would go out and that way, hit the dish and that way, hit the dish and that way, and look, you've got a car headlight or a searchlight. So think of those older cars like the Bug-Eyed Sprite, MGs, Lotus Caterhams and things like that with those sort of curved headlights. Modern cars have a curved mirror in the back as well in their lights. So do maglite torches. Okay, so anything with light that you're learning works in both directions. I only put the arrows on to show the direction that the light travels for the way I'm teaching today. But I could swap all of those arrows around, have a bright light here, and make myself a searchlight. So you now understand a bit more about convex and, I need to write it on here, concave mirrors. So that was a long and quite difficult lesson on light. I've chosen to cram it all into one video, but remember, this is not one lesson, okay? If you were here with me, and I wish you were, we'd be spending 2 or 3 weeks on this because we do a little bit at a time, and of course we do all the experiments together. So that's a video to kind of go back to and maybe take a chunk of the video and try and learn and understand it, and then the next bit. Okay, and then the next bit, and then you know everything that you need to know about how mirrors behave. Anyway, I hope you enjoyed that lesson and you can follow it, and I'll be making another one on light very soon.